Yeah, okay. So I guess if I want to start, I gotta turn the screen sharing on, huh? Okay, great. So title of my presentation of my dissertation is a computational framework for resilience informed design. And sort of hearing this title, you might have a couple questions of why do we want resilience in design? Why are we doing this? And so to motivate this, I have two examples of NASA projects where maybe we can say the system was resilient versus non-resilient. So on the left here, we have the uh, Mars Polar Lander, which was a part of the um, Mars Surveyor 98 program. And there were two big errors in this program. The first was that there was a orbiter which flew too low, which caused it to fail. That was due to sign conversion errors in the design, actually a faulty design. And then in the lander that you see, there was a problem where during its powered descent through the Martian atmosphere, the engines shut off sort of spontaneously because they think the lander had already thought it had landed. And so these faults in this situation resulted in a total mission failure for the system. So we can kind of say this is a situation where it was not resilient. On the other hand, there's the system on the right, which is the Galileo probe. This system also had faults. So it's kind of like halfway to Jupiter, they tried to deploy the main antenna that they were going to use to relay the data that they were going to collect with it. And the antenna would not deploy. And so this was kind of like, well, how can we achieve the mission in this circumstance? And because it wasn't a total failure, they were able to figure out that they could reconfigure the existing low bandwidth antenna to relay the vast majority of the data. And so as a result, the system on the right was resilient, and as a result could complete most of its mission goals. And so sort of, to motivate this, we want to achieve resilience in design in order to reduce the impact of these system faults, system hazards as much as possible. And that means both preventing known failures, but also having some recovery in the event that they inevitably occur. The idea being we can't see them all coming, but we want to be able to respond to them well if they do occur. So another piece, that you might have a question about is, well, why do we want to have a design process specific for resilience? And so in order to answer that question, we have to think a little bit more about how systems are designed typically. So often the design process is sort of multi-stage process where you first choose a concept among many, then you go and you try and design that system and fill out all the details of that, and then you go and implement the system. And if we're using, I'm gonna say, if we're using a reactive design process, one where we're not including resilience in the decision making, well, we could end up all the way at the end here in the implementation phase and be trying to retrofit the system to be resilient after we figure out that there's a need for it. And so we don't really want to do that because early in this conceptual design phase, we might make decisions that lock us into things that are going to make the system inherently resilient or not. And so what we'd instead want to perform is a more proactive design approach where right at the beginning, we establish how we want the system to be resilient. We integrate that with the system design, through the design process. And then when we actually go and implement it, we're just testing those features with everything else. And so kind of what motivates the work that we are presenting in this presentation is the idea of how do we go about this early conceptual design where we figure out how we're going to make the system resilient. Now, this is a kind of a challenging process. So if we use sort of as a motivating example, the design of a multi-rotor drone, there's actually some interesting design trade-offs between resilience and performance, that kind of make the problem a little bit interesting to wrap your head around. So for example, we could have a more resilient design architecture by going with like a hexarotor or an octarotor architecture rather than a quadrotor, which would mitigate certain rotor faults. However, in that scenario, we probably also have a heavier drone than we would have otherwise that isn't going to be able to fly as long, might not be able to accomplish as many missions. And so there's these interrelated considerations and interactions between design and resilience that might be a little bit challenging to explore without a dedicated framework. Additionally, if we have this idea of exploring these different trade-offs, often the analyses that we do to consider risk in design, such as failure modes and effects analysis, they're often these time-consuming sort of manual processes that you have experts perform. And that makes it sort of difficult to iterate over and explore trade space because each time you change the system, you have to go back to these experts and try and see, well, how is it going to fail now? And then, of course, the other piece is a lot of these analyses don't consider this dynamic resilience curve that is sort of this key to understanding resilience. So kind of our motivating question behind this work is, can we use computation to make it practical to model and explore the resilience trade space in early design? The idea being, if we instead use a computer to model the system and then explore all of these different variables, all of a sudden it becomes a whole lot more tractable to explore like a wide range of designs. So to solve this problem, we present sort of an overall framework in this dissertation where we first, get our design problem, explore different designs, model those different designs to see how resilient they are. Out of that comes some resilience attributes, and then we can quantify sort of the value of those attributes to choose a concept. Now, if we do this in an iterative procedure, what we have is sort of an optimization loop, which is good to know. And then finally, there's this question of, we're doing this all in early design. There's a lot of uncertainty and things we don't know in early design. So we might have a question like, can we even do this? Is this too subject to uncertainty or not? And so in addition, we also provide this validity testing framework that lets us determine whether the decisions we made were overly prone to uncertainty or not. And so this is something that is reflected, I guess, in the structure of the dissertation. Our first being having to do with concept selection, chapter 4 having to do with modeling, chapter 5 having to do with design space exploration, and then chapter 6 having to do with these validity tests. And so I'm first going to talk about defining resilience as a decision theoretic objective. Kind of our goal here is defining resilience so that we can incorporate it in design decisions. So the idea being, we have these models that give us these resilience curves for the different fault scenarios, and we kind of need something that bridges all of that information that we get from fault simulation with our decision making. So just to give some background before this, to talk about how risk is incorporated in design, in general, there's really two ways you can go at it. First, you can talk about sort of prevention strategies, things like reliability approaches, and then you can talk about recovery approaches, which are, what do you do after a hazard occurs? And so safety approaches get some of those things. Also, additionally, there's some overlap between these in the field of prognostics and health management, where we're looking at proactively mitigating and proactively preventing hazards from occurring. And kind of one key thing that I guess is sort of a definition that's used very commonly in a lot of these risk-based frameworks is that risk is multiplication of probability and severity. So it's sort of like an expectation of how severe the consequences will be. Now, that talks about including risk in design in general. There are, of course, specific considerations having to do with resilience that have been explored previously. So generally, when we talk about the resilience of a system, we're talking about the curve of faulty performance that occurs after a hazard, after the system experiences a hazard. And so you can imagine that curve would be better if it recovered sooner than if it didn't. And this whole definition of resilience in the literature is often called the resilience triangle. And different people have quantified different metrics in terms of the robustness of the system and the recovery time. And so, our goal isn't necessarily to compete with these terms for resilience, but what we want to do to incorporate it in decision making is consider the risk associated with resilience, which means considering both this curve, but also thinking about, well, how bad are each of these scenarios compared to each other and on the net. And so in order to do that, what we came up with was developing an overall cost model for the set of scenarios that a system might encounter. So the idea being each of these resilience curves, we give some sort of cost function having to do with the consequences that occur in that scenario. And then each of those scenarios, just based off of how likely they are, get different probabilities also. And then we can define this overall cost of resilience as being the expectation of of the scenario cost, which is like a weighted sum of probability times cost, which is the same as that definition of risk that I put forward a couple slides ago. So, because we're interested, of course, in quantifying resilience costs, and we developed that scenario cost model, a part of figuring out what those costs are should be taking what we get out of this resilience curve and figuring out, what's better or worse. And so what we do to incorporate that in design is we we develop this overall, I guess, form of a cost model, identifying the different costs that could result from a simulation result like this. And basically the general form has a few different things. The first being repairs being, at some point you might fix the system and get it back to nominal. That will probably cost something. And then there are performance losses, which is in the time between it failing and you repairing the system. It probably has some faulty performance curve that you want to quantify the cost of. And then finally, just the hazard occurring might also result in some sort of disruption of the system that you want to give some sort of cost to. So this is the general form of what you might use for an expected cost of resilience function. We have two adaptations that we develop in this chapter. The first being for IBFM models that is a previous modeling framework that was developed in the lab. We also developed another adaptation for the models that we introduce in the next chapter, and I'm going to talk through that adaptation in the next couple slides. So kind of what we realized, I guess, when we were developing these expected cost frameworks was that in order to quantify this expectation, we have to have this set of scenarios that are injected in a fault simulation. And so actually quantifying our expectation accurately results from having some sort of fault sampling approach that we use for each hazard. And so what we developed in this chapter to go with these models was a model that has to do first with the set of fault modes, and then has another set of rates for the set of operational phases that the system goes through. And then within each of those phases, we can imagine there's different times when we can simulate faults. And so there's another set of another part of the model that is these in-phase samples. And so kind of what we came out of this with was we had this question of how can we best sample a model to accurately approximate the expected cost of resilience while minimizing computational cost. The idea being, if we want to iterate on a cost model like this quickly, we don't want to sample too many scenarios, but at the same time, if we don't sample enough, it's going to be inaccurate in some way. And so we did this study of different fault sampling approaches. I can't really go into all the details of it, but essentially at a high level, what we found was that no matter how many points we used, numerical integration approaches performed a lot better than Monte Carlo sampling. We then tried different numerical integration approaches and found the FAIR2 quadrature to minimize error compared to some of the other quadratures we could use for numerical integration. And then we had this idea of, well, what if we set up this fault sampling approach based off of prior function knowledge that we had that, the resilience curve is going to look a certain way. And what we created this approach and we were able to increase the efficiency, but the problem with this approach that we found was that if we change the design, all of a sudden the form of that resilience function changes also. And so we get inaccuracy in our fault sampling approach. So in conclusion for this chapter, what we went through was that resilience can be defined as an expected cost so that it can trade the risk of resilience with design and operational costs. However, if you quantify an expected cost this way, you have to develop a fault sampling approach for your model that consists both of a set of fault modes and injection times. And so if we actually want to use this metric effectively, then we have to have some balance between the computational performance of that approach and the accuracy that we want out of it. So in the next chapter, we then study how to simulate resilience curves in early design. Sort of the objective there was to create a toolkit for early functional hazard assessment that simulates dynamic behaviors. This work was actually a collaboration with my classmate Hannah Walsh, who defended her PhD about a month ago, also works in the lab. And just to put this all in context, if we think about the design process as something where you go from task clarification, conceptual design, embodiment design, detailed design, there's kind of a parallel process that occurs in hazard analyses that are often used in the design of aircraft and things like that, where first they define the requirements having to do with risk, then do a functional hazard assessment, preliminary safety assessment, system safety assessment. And so kind of to put our work in context, we can sort of put these in two different types of simulations. And so those would be early stage fault simulation and late stage fault simulation. And kind of the idea with these late stage fault simulations is that you sort of already have a pre-existing detailed model or design. It's almost fully specified, at least in terms of the design architecture and all of that. And so sort of the purpose is to make whatever small changes that you can to the system to assure safety, and then also just to quantify in the system that you already have, how safe is it. Now let's contrast that with maybe this idea of early stage fault simulation, which is more what we're trying to do, which is that in this situation, our design model is a whole lot lower fidelity. And instead of like making small adjustments to the design, we're trying to choose like totally different concepts with it. And in order to do that, we kind of have to model the system at a high level. And so this is a distinction we make between this work and sort of a lot of the work that's out there in the research in terms of fault simulation, is that we're trying to do this early stage fault simulation rather than some of these late stage fault simulation approaches. Now, of course, there have been previous approaches in the literature for early stage hazard analysis that often involve fault simulation. The first, you might call these discursive approaches. These aren't necessarily simulations, but they are this sort of process where people go through and they look at sort of the functions that the system is going to achieve, and then look at the different failure modes that are supposed to occur and sort of see what the effects of that will be, and then try to mitigate it somehow. Kind of the limitations with these approaches is that there's not really a representation of that dynamic effects. And so if we're wanting to consider the resilience of a system, it's a little bit limited in terms of that. The other piece, like we talked about in the introduction, whenever you're using sort of a manual process like this, it can be a little bit difficult to iterate over in design. So if we want something that we can explore really large design spaces with computation, we'd prefer to have some sort of computational model. Now, additionally, there are model-based approaches in the literature. So, so this has been done before, of course. Now, sort of the limitations with the previous model-based approaches is generally they either rely on existing simulations, or they sort of require the user to define a model sort of in a base language by themselves, which is a little bit difficult because then your user also has to define this whole simulation framework for it. And there's not really very many existing dedicated simulators for modeling resilience specifically. And so what we'd like to do is create a modeling, simulation, and analysis environment for these early functional hazard assessment type analyses that let us simulate these fault resilience curves. The idea being there's not really a tool out there to enable this yet. People have done different things, but there's not really like a thing to help you do it. And so in order to solve this problem, we create the FMD tools modeling, simulation, and analysis framework. And in this process, you first construct a model, simulate the faults in the model, and then create different analyses based off of those simulations. One of the key features of this framework is that you can use different levels of design representation through the process, sort of as they are appropriate. And so starting with like a high level network structure all the way down to some hierarchical dynamic model of the system. And that lets you go through this early design process where the design may not be very detailed necessarily. So to talk through, how this actually works when you implement a model like this, first you create different classes which define the behavior of the system. Then you connect those functions together with flows in an overall model class. And then you create this sampling approach, which we talked about in the first chapter, which is which faults do you want to put in the different behaviors of the system. After you sort of set that all up, this is then sort of given to the simulator, and the simulator goes through each of those fault scenarios, runs the model through until the time when the fault occurs, injects that fault, and then runs through. And as a result, you get this whole set of model results for each scenario, looking at sort of like the resilience curve that occurs in each of those circumstances. And then finally, based off of those simulations, we can then analyze the resilience of the system. And so again, if you look at the chapter, one of the examples that we use for this is this drone model that we talked about in the beginning. And we sort of go through the different analyses that you can perform, things like network analysis and graph visualization, static and dynamic failure modes and effects analysis, or functional hazard assessment, visualization of the propagation of faults. And then of course, we're wanting resilience. So looking at the nominal and faulty plots of system performance over time. And then finally, expected resilience quantification. And in our example of this that we have in the chapter, we sort of use this to compare different architectures. And kind of what I want to illustrate in this example is that we have this ability to represent the model at increasing levels of fidelity as we sort of need to by the design process. So in conclusion, in this chapter, we presented the FMD tools modeling, simulation, and analysis framework. This toolkit enables analysis and simulations to consider resilience in early design. It's also sort of like freely available. So if future researchers want to build on it, they can sort of download the code and extend it however they want. Additionally, we had examples in the chapter, first of the drone model that I showed showed how you can increase model fidelity through the design process. And then there was another example that I didn't get to show that was an integrated fire propagation and response model, which showed sort of our ability to extend this framework to very complex simulations. So after we went and talked about modeling the system, I'm now going to talk about how you can explore a design trade space in this overall framework. And sort of the goal here was using computation to exhaustively and systematically explore the coupled design operations and resilience variables. And in order to achieve that goal, we sort of pursued the objective of formalizing the optimization problem that we're trying to consider here, and then exploring different architectures that you might use for efficient solution of this problem. And this work was also a collaboration with Arpan Biswas, who just defended his dissertation Friday. So if we consider, what has been done previously in optimization of resilience, one of the big approaches that has been pursued previously is we kind of call a sequential approach in this work, where first you have this sort of top level system-wide resilience allocation, where you have these different subsystems, and then you allocate sort of target levels of resilience to each of them. And then after that resilience problem is done, you then solve at the subsystem level problems, trying to achieve each of those targets. Kind of our hypothesis in this work is that this doesn't, if you go through an approach like this, it doesn't really connect the loop between the upper and lower level. And so there's no valuation of like the flexibility you get from redundancy at the top level that can then be used by the resilience policy at the lower level, and vice versa. There have been other examples of different architectures put out there for resilience also. So there's this idea of two-stage optimization. While this is a one that's been widely explored, it's kind of only applicable to a specific type of resilience problem, where you can optimize the full set of resilience variables post hazardous event. And so we actually are wanting to consider a different type of problem, which means we don't actually include this in our comparison. Another piece, another approach that's been put forward in previous work is the bi-level architecture. There have been a couple of examples of this, but it hasn't really been explored in depth. And then additionally, you just have all-in-one structures that are put out pretty commonly, usually over just like one set of variables and not one of these combined design operations and resilience optimization problems. And so one question, that we kind of are trying to solve that hasn't been presented in the research before is, do some of these approaches perform better or worse in terms of effectiveness and efficiency? And if so, how can we improve the performance of these different solutions? So in order to run this comparison, we first have to define the problem that we're trying to solve. And so here at the left, we have a general formulation of the optimization of design operations and resilience. You can see there's kind of just a generic form where each model you're trying to optimize a cost subject to inequality and equality constraints. And, there is kind of a relationship. The design model, you only optimize design variables. The operational model is a function of both design and operational variables. And then the resilience model is a function of the design, operations, and resilience variables. And the one other sort of thing that we have that specifies the form of this model is that the resilience cost function for the resilience model follows the form that we provided in the first chapter, which is that it's this expected cost of a number of different scenarios. Now, solving this problem has its own difficulties. One thing that we use sort of as a assumption in this work to make it a little bit easier and also to fit within our overall framework where we have models is to substitute each of these equality constraints, which we consider to be sort of like a simulation or a model where you have some input decision variables and they give you some output response variables. Now, if we perform that solution, we get what you might call a multidisciplinary feasible formulation of the problem, where we have the same problem, but instead of equality constraints, we just have inequality constraints. And what this gives us is the ability to have sort of an all-in-one architecture where we just sort of run each model in sequence. So At each step, we give the design model a set of design variables. It outputs some variables. Those outputs go into the operational model along with the design and operational variables, which in turn go into the resilience model along with the design, resilience, and operational variables. Now, if you go through this in a loop, you have sort of like a optimization process, which you can use with any sort of algorithm you want. And so this is just sort of how you would solve this in an all-in-one framework. Now we additionally then create variants of that framework. First is sort of the sequential approach that we saw in previous work, where first there is an evaluation of the design and operational model and an optimization of those two models. And then afterwards, you take the optimal solution from the design and operational model and run a optimization of the resilience model in the optimization of resilience. We can call these two optimizations sort of like a first stage and a second stage. And essentially what is going on here is you're optimizing the resilience of the problem after you optimize the design and operations. In the bi-level approach, on the other hand, at each evaluation of the model, we first put in a set of variables in the design and operational model. And then at each instance of upper level design and operational variables, there is a lower level optimization of the resilience variables for that design and operational policy. And so, we can call this an upper level and lower level. And in this case, the optimization of resilience is actually nested inside the design and operations optimization. And sort of one of the nice things about having architectures like this that separate the design and resilience optimization, like the levels, is that it lets you run different solution strategies at each level. And so in this work, we created a lower level decomposition of the resilience model where we decompose the different subproblems that are related to different subproblems where different sets of variables are related specifically to different sets of scenarios that we run in the model. And then what we can do is we can optimize each of those either in sequence or in parallel, but they run with a lower dimensionality. And then after that, if there's a set of scenarios that are not connected to any variables, we execute those. And that gives us the full cost of resilience that can then be used in the upper level optimization in the bi-level structure. And the idea basically of using this is that reduces dimensionality of the lower level resilience problem, which is the main source of computational cost. So again, in order to demonstrate this, we considered the optimization of a drone system where we first took the system, created a model of the design, operations, and resilience costs in our simulation framework that we defined in the previous chapter. And then right at the beginning, we just sort of explored the design, operations, and resilience trade space to sort of make sure it was an interesting problem. And yeah, we found trade-offs between architecture, height, and different contingency actions we could leverage that we thought would make it a good problem to compare different architectures. So then we went and we did this comparison, and what we found was that, of course, sort of like we expected, the all-in-one architecture is the slowest architecture, but it does in fact find the optimal solution. The sequential optimization, sort of like we hypothesized, is the fastest because there's only two optimizations at the upper and lower level that it has to run, but it doesn't necessarily find the optimal solution because it doesn't value the flexibility. And then additionally, we have this bi-level approach. It can decrease design and operational model evaluations, but it doesn't have quite as big of an effect on computational costs. However, when we use this lower level decomposition of the resilience model, which reduces the space of the problem, we get a much lower computational cost because of the fewer evaluations and the lower dimensionality. So in summary, in this chapter, we formalize the optimization of resilience with design and operations in a unified framework. And then we compared different architectures within this formulation of the problem. And we found that first, sequential approaches have low computational costs, but they don't necessarily converge to an optimal design. We sort of think that probably in order to work, they need some sort of upper level surrogate of resilience costs to be effective. And then additionally, we found that bi-level architectures can decrease computational costs, first by reducing upper level iterations, but also by enabling you to use different solution strategies at each level. Specifically, the one that we put forward is sort of this idea of decomposing the lower level into independent sets of variables and scenarios. So finally, we had this overall framework for design that we wanted to leverage. And we had this idea that we were using it in early design. And given all of the different uncertainties that might occur in this, when you're leveraging a design framework like this, when you don't know a lot about the system yet, is determining whether your decisions are actually going to be valid given that wide space of uncertainty. And so our final objective here was to quantify these uncertainties and then perform tests on the design process based off of thresholds that we set up for the way the uncertainty affects the process. Now, there have been previous approaches to considering the validity of design processes. So one of the big ones in the design literature is this idea of the validation square. Our work fits totally fine in this sort of, however, what hasn't necessarily been addressed in this work has been, how does it factor specifically into resilience-based design, and how does uncertainty play into the validity of the design process? And so what we're trying to test is just sort of one piece of this validation square, and it's answering this question of how well does a design process perform empirically, given there is some sort of effective uncertainty on the process. And so in order to create this testing approach, we first define a set of uncertain, a space of uncertainty for our assumptions. We set up different test metrics for how the design process was supposed to go. And then we propagate uncertainty through the model that we set up of the costs that we use to make different decisions. And then we check those different test results, and based off of the metrics we quantified, we can sort of say, well, this process passed or failed. We defined 3 tests in this work, the first being the uncertainty check, which basically asks the question of, if you consider all of the uncertainties, would your optimal be different over that space of uncertainty compared to the design process where you did not consider all that uncertainty? And of course, given that there might be small changes that you might might make this is within a desirable threshold, because it might always be different when you consider uncertainty, but if it's not a big difference, you probably don't care that much about it. An additional tests we have here is the value improvement test, and this is just sort of did the expected value of the design increase from the initial design? So you can imagine if you go through all this design process and you start somewhere and you end somewhere, and your ending design isn't actually that much better than your starting design, maybe that process was a little bit invalid in a certain way because you didn't effectively explore the trait space. And then finally, we have this idea of a meaningfulness test, which is basically looking at if you're making the choice under too much uncertainty, or whether you should wait to reduce the uncertainty before making the choice. And this looks at, how much better would the design be over the space of uncertainty if you were able to reduce it before you made the decision. And so these are our tests. And in this chapter, we had a couple of examples. One of them was this example of electric power system design, where we first set up this model, created sort of like a cost model around the redundancy of the system in terms of design, operational, and resilience costs. And that gave us a certain set of results, right? Of this is the optimal system. And then what we did was we defined then, here are the uncertain assumptions that would affect this process. And we had, different uncertainty models that we used for that. And then based off of that propagation of uncertainty through the model, we were able to determine that we passed these tests because, one, the design did not change over the space of uncertainty. Two, the increase in design value was very high, sort of in comparison with everything else, even over the space of uncertainty. And then three, the amount of loss that we had for having the uncertainty in the design was not very big in comparison. And so because the effective problem uncertainty was small compared to the value of the design process, we sort of concluded that that was a valid design. So in conclusion, in this last part, we presented an epistemic uncertainty-based validity testing framework for early resilience design processes. And we showed examples. Of course, in the slides, we have the EPS example of a continuous uncertainty-based validation process. We also have in the chapter a discrete testing process. Of course, in the slides, we have an example of it passing, but if you look in the chapter, we also have an example of it failing, just so you can see how this all plays out in terms of how you might leverage this in design. So in summary, what we presented in this work was an overall design exploration, modeling, and concept selection process that had additionally this sort of validity testing process that we could then leverage on it to see when we can use this appropriately. And one of the, it's important to note, of course, that this overall framework is embodied in each of the chapters of the dissertation if you want to read more. But in a lot of ways, it's not like we were able to cover every single question. And so it's good to think a little bit about, how might we actually build on this work in the future? What future research questions might be interesting to look at based off of what we already set up here. So in the first piece, we had this idea of choosing concepts based off of the expected cost of risk. Of course, there's also often in design, we have to consider external requirements that are given to us from regulators, from people who are interested in safety. And so kind of a question for this work is, how do we, when we're using a cost framework like this, also incorporate these sort of safety related requirements in our decision making? An additional piece, we talked about the modeling of systems. Of course, our framework there was fairly, has some limitations. So for example, considering dynamic uncertain assumptions in the model, it's a deterministic model. And so one future area of research would be figuring out how to incorporate stochastic variables in a model like that, while keeping our sort of high level representation of the system. Additionally, we just outlined a couple architectures. I think it would be an interesting area of study to look at additional formulations to additionally structure the integrated resilience optimization, sort of looking at if there's different assumptions that you can use that then give you a more efficient design. And then finally, we add this idea of validity tests on the design process. And for me, it's kind of an interesting question. We did this afterwards, but could we use it instead to motivate the design process? So can we sort of define a zone of problem validity or some rules of thumb that we can sort of use before we go and do design that can sort of help us set up the problem to be valid afterwards? And so this is the conclusion of the presentation. I just sort of want to go through, of course, this came out of the different papers that I worked on over the course of the dissertation. Of course, I have references here. And so now I can open it up to questions.
Great job, Daniel. So for, I guess, those of you who are maybe not as familiar with this process, we're going to have some time for our external audience to ask questions, and then we're going to go into the exam session with just the committee members. And I was also, I wanted to thank all the NASA colleagues and Park colleagues who've joined, and maybe give you all an opportunity to ask questions, and of course the students and other people on the call.
Good.
I can get started.
Sure. Thank you.
Daniel, really important work and truly impressive compilation of activities, and I must say this is really awesome. I mean, this really could change how we go about design. So I'm glad that that you made as much progress as you did. I have two questions. One is about validation. So in the end, if you choose a design, how do you know that this is truly the right thing and not a different one? How would one, do you have any thoughts on how one would go about validating that?
So you mean the design itself?
Well, I mean, yeah, I mean, the design ultimately turns into something that you built, right?
Yeah. So kind of the test we set up were for the design process. Now, if you have questions about the design itself, there are of course different things that you want to consider about what you actually ended up with. So first, we have this idea of verification, where you sort of look at, does the system actually perform like you specified it early on, right? So is the system achieving its intended functionality? Does it behave in the way that you expected? And then there's the idea of validation, which is, does it actually solve the problem that you wanted it to solve, you know, and achieve sort of the performance that you wanted to. And so if you're looking at the design and not necessarily the design process, I think those are the typically what you would want to answer about the design itself being a valid design. Does that answer your question?
Yeah, I think in part. I'm just wondering, how would I convince a manufacturer to build the design that you essentially identified as being optimal, right? So what assurance does a manufacturer have that it is truly the optimal one?
Mhm.
Yeah, so you know, I think that's just sort of a process of checking, and then when you actually go and implement and prototype the system in the embodiment design process, you do way more analyses than you do in the early design process, and so you have a much more detailed understanding of the system than you would otherwise. Of course, you haven't done that necessarily for all of the different design alternatives, you know, that you considered early, but you can have some idea that at least that the system is feasible. And if you trust what you did in early design, and maybe you prototype some of those early designs to some degree, hopefully out of that you were able to get some data that you can rely on if you're like truly interested in like totally answering this question.
Okay, thanks. The other question I had was regarding to the health management functionality that you suggested to implement, in particular diagnostics.
Yeah.
I'm curious, how would the whole resilience setup change if you also added a more forward-looking element of health management into that, you know, specifically prognostics?
Yeah. So are you asking how it would sort of affect this overall framework, or how you would incorporate that in this overall framework?
Yeah, a little bit of both, really.
So, you know, I think the prognostics is looking at, generally when we're looking at resilience, we're looking at this, we're looking at what happens post-hazard, like recovery, right? If you're doing prognostics, you're trying to prevent it from happening, right? And so the model that you use then is changing the probabilities essentially of each of these hazardous scenarios. And of course, the actions that your prognosis, you know, your health management system takes as a result of that might add new scenarios for, you know, the actions being taken, you know, in terms of maintenance or taking the system offline or something like that. And so, you know, probably the easiest aspect of it would be changing the probability model. If you want to go into more detail, though, you might actually look at modeling the degradation processes in your probability model to sort of then see how these prognostic systems perform given certain thresholds. So it just sort of has to do, I guess, with how much detail you want to spend on the prognostic systems, because you could go into a lot of detail in terms of modeling if you want.
How would you how would you incorporate the fact that the prognostics themselves may not be perfect, also that they have only a certain probability of whatever they're predicting?
Yeah, so that gives you that means you have to change your fault sampling approach to consider joint failure scenarios where maybe you have a hazard that is going to occur, and then you have some you have a scenario where the prognostic system does not catch it, and a scenario when it does catch it. And then of course you have you have scenarios where maybe you started out with nominal system and there was no hazard to occur, and your system just does maintenance by itself by accident, right? And so in order to consider how to use prognostic systems in a design, if you want to go sort of into the effect, it would be introducing those fault scenarios into the design. And of course, those have different probabilities that are going to change the overall cost of risk.
Good, thanks. Other questions?
Chris, it's Guillaume. I have a hi. I got a question. I promised a complex question to Daniel.
Oh no.
No, not that tricky. Don't worry. It's so I'm intrigued by so you play a lot with like the uncertainty. You explore basically the uncertainty space in your design and trying to optimize for resilience. So I was thinking, what if you have a scenario where the system is like a major infrastructure, like let's say the biggest one I can think of, the more complex one I can think of is the national airspace that evolves
right.
Over many years. So, and let's say I'm at the beginning, I'm designing it. So I have a set of design options.
Yeah.
But there are also some that I know because I looked at what's been done in research that might come up in 5 to 10 years, or other ones that are just a hint of an idea yet. So maybe they'll mature into something in 20 years, maybe nothing.
Yeah.
How can I take that into account to actually build from the start a system that can evolve more easily to incorporate those new technologies over time?
So yeah, so I think the word for what you want in the system is flexibility, right?
Yeah. Or evolvability or flexibility, as you wish.
Yeah. So now in terms of how do you get that in the design, that's a little bit more of a difficult problem, because you sort of have to be able to plan out how it's going to evolve potentially in all of these scenarios. So of course
or plan out that it might evolve. We don't know what form it's going to be.
Yeah, so I mean, if all you're looking at is just the operational performance or what the value of each of these things might be, you might figure out some sort of event tree, right, of how the system might unfold over time, right? And then you can sort of say then, well, this scenario weighs so much into the implementation of the system that we're doing now. This scenario weighs in so much into the implementation of the system that we're doing now. And you can sort of take all of those future potential considerations and kind of use them early. It's not now, there's probably a lot of different ways you could do that with more or less detail, but that's sort of the general approach I think you'd use.
And at the beginning, so at the beginning of presentation, did I hear well that you can kind of perform that optimization with unknown parts of the system.
Mm.
Is that right, or is that something that I read too much into?
So,
Like a partially known, basically.
Right.
I mean, ultimately what we're doing, like if we're in early design, we have not designed every detail of the system is sort of, I think, what I was trying to say there. And so, yeah, we're running an optimization sort of on as much knowledge as is practical to have in early design, which may not necessarily be, you know, there's probably unknowns that affect that. And that's sort of why we had that validity testing process at the end of like, well, what if we quantify these unknowns and see if they affected what we did very much. So
specifically, which of the validity tests would be applicable? All or some?
yeah, so I mean, all of them would be, because those unknowns would be uncertain parameters or assumptions that would then factor into every single test. But you know, I think the main consideration, or each of them sort of factor into it. I think one of the main considerations would be, you know, do you try and figure out what that unknown is better? Like, do you try and characterize it, or do you sort of wait? And, you know, of course, sometimes if it really is like an unknown, you may not be able to characterize it better. And so in those situations, you just sort of have to look at the expectation of what do you expect to happen in the different scenarios that unknown could cause.
Okay, thanks.
Yeah, of course.
Any other questions from the general audience? Good. Well, if there's nothing else, I think we can move on to the committee only portion. Again, thank everybody for coming. I see Chaitan's here, Guillaume, Kai. Thanks for joining. It's great to have people outside of just our OSU ecosystem also viewing this work. I will post this on. I'll send out an email. We have a YouTube site. I'll post this afterwards if you want to come back and look at it, or show somebody else. It'll be publicly available. So, so thanks all for coming, and again, thanks to all our collaborators here for helping shape the work here. I'd like to thank NASA for the funding throughout the years that Daniel's been here, for supporting this work as well. That's been great and that was a big factor in Daniel, being very productive on this topic as well. So thanks again.
Yeah, of course. Thanks everyone for attending. It's nice to be able to share my research.
Yeah. Great.
Good job. Very nice work.
All right. Thanks.
Right. Thanks. Bye-bye.
Right.
Bye.
Thank you.
Thank you.